Next we ask about a point on the unit sphere of radius 1 centered at the origin. The point on the sphere corresponding to the point 0, 1/2 in the xy plane. Now, of course, if we're on the sphere, x squared plus y squared plus z squared is 1, something you should have encountered many times by now. So that if x is 0 and y is 1/2, we determine that z is the square root of 3 over 2. So that we're talking about a region in the xy plane near the point 0, 1/2, 0, and maybe I should label that. So we have down here the point 0, 1/2, 0 in the xy plane, and a rectangular region surrounding this point. And we think of a much smaller rectangular region than the one I've drawn. We think of a region that becomes infinitesimal, becomes the dimensions both approach 0. So that any point within this tiny rectangle will make at any point within this tiny rectangle, the corresponding point on the sphere will make an angle of approximately equal to the angle of the normal vector at the point 0, 1/2 square root of 3 over 2. In other words, we have the point 0, 1/2, 0 corresponding to the point 0, 1/2 square root of 3 over 2 on the sphere, and we use this point as a basis for determining the normal vector on this tiny region. And then, of course, we take limits and we get integrals. Now, in this case, we're not going to take limits of this expression, but we want to see what the normal vector would be. And it should be clear that the normal vector, because of the symmetry of a sphere, points straight away from the origin. So that the vector from the origin to 0, 1/2 square root of 3 over 2 can be used as a normal vector. So that we would get the vector 0I plus 1/2 j plus the square root of 3 over 2k. And that turns out to be just 1/2 j plus the square root of 3 over 2k, because of course the x component of that vector is 0. We could also get the normal vector, and this is very important because generally you're not going to have the symmetry of the sphere, and you're not going to be able to simply say, well, it's just going to be radial. That's only for spheres. Okay, so if we didn't know that, we would say, okay, the sphere is the level curve x squared plus y squared plus z squared equals 1, or x squared plus y squared plus z squared minus 1 equals 0. The normal vector is then the gradient of that function. Okay, if the sphere is a level curve for this function, then the gradient is going to be normal to the curve, to the surface, and the gradient is very easily found to be 2xi plus 2yj plus 2zk, which comes out for this point I'm going to write this out very explicitly at 0, 1/2 square root of 3 over 2. X is 0, so we get 0i. Y is 1/2, so we get 1j. And z is square root of 3 over 2, so we get square root of 3. It should be square root of 3k. I hope nobody copied that down the way I wrote it, but this should correct that, okay? Either way, if we calculate the magnitude of n divided by the magnitude of n dot k, which, as we've seen here, especially here, is the ratio of the area on the surface to the area down in the plane, the xy plane, we get 1 divided by square root of 3 over 2, or 2 over the square root of 3, which is slightly bigger than 1. It's about 1.1 something, 1.13 maybe. And this tells us that the area of this region up here with its slight tilt, it's significant tilt but not great, is about the square root of 3 is 1.732. That differs by it's about 1.14 times the area of this rectangle down here. So if we want to get the surface area of this sphere over some region of the plane, and in this case we're asked to find the integral for the surface area above the square with vertices at 0, 0, 1 half, 0, 1 half, 1 half, 0, 1 half. I think I said all of them right. Our integral would just be this of the magnitude of n over n dot k. Okay, the magnitude of n, well, this will be, let's take this to be our normal vector. And then n dot k would be what? It would just be 2z, because I dotted with k is 0, j dotted with k is 0, 2z k dotted with k is just 2z. So our expression here would be, turn out it would be 2 times the square root of x squared plus y squared plus z squared. You can verify that that's the magnitude of this vector. And then you divide that by 2z. And you could simplify that to x squared plus y squared plus z squared over 2z. And there's a little more that we need to do with that. And I think I've got that right back here. And, okay. Ignore everything to the left of this line. So if your point in the plane is x, y, 0, then the point on the surface is what? X, y, square root of 1 minus x squared minus y squared. It's x, y, z. X squared plus y squared plus z squared is 1. It follows that z is the square root of 1 minus x squared minus y squared. Using 2xi plus 2yj plus 2zk for the normal vector. This is just what I said a minute ago, but I've written it out. Then this expression, this area ratio between area down in the plane and the area on the sphere, depending on the tilt of the sphere, is going to be this. And of course that simplifies to this. So our total area is this integral, same integral I wrote down here, but now I've replaced the magnitude of n over the magnitude of n dot k by x squared plus y squared plus z squared over z, and we integrate with y, and with respect to x, it doesn't matter which is first, the limits in both integrals are the same, and they're fixed, they don't depend on the other variable. The y limit doesn't depend on the x variable, the x limit doesn't depend on the y variable. Now, we have a problem. We can't integrate this because z depends on x and y. So we can't just treat z as a constant. So what do? Well, we know that z is the square root of 1 minus x squared minus y squared. And we also know that the square root of x squared plus y squared plus z squared is 1. So that what we get down here, again, this is because we have the sphere x squared plus y squared plus z squared equals 1. We're on that sphere. We're talking about the surface of that sphere. So this expression in the numerator is 1. This expression in the denominator is the square root of 1 minus x squared minus y squared. And then we simply complete that integral. We use trigonometric substitutions. And we get the result. We get the area of the sphere above that 1/2 by 1/2 square in the xy plane.